Hey everyone, my name is Chris and I'm from FlipMath, and I'm going to take you through today's topic, which is
Dun, dun, dun.
differential equations. It's an A2 maths topic for the C4 paper. It's in nearly every C4 paper there is, but I'm going to be talking about it pretty much, and I teach from a CA perspective, Northern Irish board, but it should do for each. Okay, the objectives of what we're going to do today, and I should bear in mind today is this video is a recap lesson, not meant to replace a full lesson, but to go over many of the cliff note ideas of how to handle differential equation questions and the strategies involved in solving them, but shouldn't replace a full lesson or the notes that you can also find and download from the website at flipmath.co.uk. We're going to set up differential equations from a set of instructions, find the unknown constants k and c using given values, or the values that have been given in a question, and solve problems using those different differential equations. Introduction. So, differential equations are basically questions given with the expressions of a rate of change. So they're given as a differentiated term as in the question or in the expression that you're given. Now, remember, one interpretation of differentiation is that it can be described as rate of change, but rather than one interpretation, the way that most people think of it, and most people use it, is that they are finding the gradient at any point along a curve. Well, the gradient is just a rate of change of y with regards to x at any point along a curve. So a gradient itself is a rate of change, but many of the examples that you see in differential equation questions, it's some sort of modeling problem where one thing's changing over time specifically, or something to that end. So I'm going to set this out as a number of objectives that we're going to try and accomplish. I'm going to take you through each one individually, and then I'll put them all together in a couple of questions and see if we can put them together, as well as modeling some problems that we've got. So the first objective we're going to look at is that we're going to rearrange that rate of change expression or equation to an expression that we can integrate, or to a form that we can integrate, for the main reason that ultimately in a differential equation question we're trying to find an original equation linking the two variables so that we can problem solve. So rather than an expression for the rate of change, we want one that defines y in terms of x, or whatever the two variables that you have are. So if I consider the following example. A boy is tracking his progress in a video game. The amount of XP he gains, x, can be modelled over a period of time t in hours using the following differential equation. dx by dt equals kx, where k is an unknown constant, or just a number if you like. So his XP changes over time in some sort of relationship such that it's some number times the XP. Remember that integration takes place when it's in the form of integral with respect to a variable. I've put delta t, or with respect to t, in this case, but it could be with respect to any variable. So I just can't integrate both sides, because on the left we have a dx and dt together, and there's some sort of confusion there. So what we need is an expression just with the dx and the expression with the dt. And the way we achieve this is we need to split up any variables that belong with them, and they should go with them. So this can be sometimes a bit confusing, especially when trying to explain to people. So if I go to the example I've got above and highlight the dx and the x, they are the same variable. They are both x terms if you want. So once the dx means with respect to x, and the x is just the variable x. You'll notice that there's not a variable for t. So in many cases for these differential equations, the k will go with the delta t, or the respect to t, on the right hand side of the equation, so that if something to integrate, otherwise it would just be 1 on that side. Okay, and we move the terms like such. So the delta t will multiply across, and the x will divide across, something like that, using your basic rules of algebra. And once we're at this point, we can stick integrals at the front, because we've got one term. The left hand side's with respect to x. I can integrate that with respect to x, and I can integrate the k, or which is just a number, with respect to t. We now have expressions we can integrate, and we have completed our first objective. Objective 2. We're going to integrate the expressions because that's what we set out to do. So it gets us a step closer to finding our initial expression linking x and t. So we've got the integral of dx over x equals the integral of k dt. Reminder, the integral of 1 over x is natural log of x, and the integral of a number is just multiplied by the variable you're integrating with respect to, in this case t. So if we integrated the number 2 with respect to x, you would just get 2x. In this case, when we integrate k, we will just get kt. So when we integrate on the left, because there's no limits on it, we'll get natural log of x plus some constant. We don't know what it is, but if we differentiated that constant, it would just disappear. It could have been there, but we're not sure. Same thing on the right, we will get a constant. Now, we get two unknown constants here, a and b, which when we integrate, well, the easiest thing to do is just bring them over to the other to one side. It's because they're basically both numbers. Basically, if the one on the left was a 3 and the one on the right was a 5, we'd bring them together, and the 3 would become a minus 3, and we'd get just one number at the end. We call this combination of a and b a new constant c, and we write this expression that we've got as natural log of x equals kt plus c, where we'll basically take this a, bring it over, so we'll have b minus a, and b minus a equals c, but in general case, rather than thinking of two separate constants when we integrate a differential equation, we'll just get one. We must now find the values of the constants k and c, which is the second learning objective from earlier on, and we have integrated our expressions successfully. Okay. Objective 3 is going to be to substitute in values to find those unknown values k and c. The reason being that this will give us our expression linking x and t. The question would also continue and give us some additional values here, so I'm going to give you the rest of what that question would have been. Given that the boy starts with 100 XP in the game, and that after 2 hours he has 1200 XP points, calculate how long it will take him to reach 100,000 XP. Initially, or given that the boy starts with, means that time is equal to 0 or t equals 0, so we can substitute in t equals 0 and x equal to 100 into our expression, which was natural log of x equals kt plus c. Once I put those in, I'll have natural log of 100 equals k times 0 plus c. 0 times k gives me 0 and just cancels out, giving me that c is equal to natural log of 100. That's c found out. We can also substitute that t is equal to 2 and x equals 1200. 1200 is the number of XP and t is equal to time in hours. Into the expression, natural log of x equals kt, and instead of plus c, we just found plus c to be natural log of 100. I'm going to make that natural log of 1200 equals 2k plus natural log of 100. Move the natural log of 100 to the left so that it becomes minus natural log of 100 equals 2k. And using our laws of logs, that says when we've got logs of the same base and we take them away from each other, that is the same as when you divide one by the other. And 1200 divided by 100 gives me 12. Natural log of 12 equals 2k, giving me k equal to half of natural log of 12. Now, you should keep it in that form, although some people like to work in decimals, and if you do, you would have got something like 1.24 to 3 significant figures. Word of warning though, if you're going to round, don't round too early. 3 significant figures at that stage, unless it asks for it in the question, find the value of k, for instance, where, in CA terms, you'd always give the 3 significant figures. Leave it as the natural log version, so the half natural log of 12. It means that when you come to the end of the question, you can pop it all in as one go and only do the rounding once at the very end, rather than rounding at this stage and then using that rounded value. It just affects your accuracy just too much. I would also say that if you're desperately wanting to use decimals at this stage, take it to a much higher degree of accuracy. But again, if you go to 5, 6 decimal places at this stage, does it look any simpler than what that is there? And those are values of k and c. Objective 4. We're going to solve new problems using that new expression. And the reason, because it gets you marks. The end marks of this question are involved in solving this together. We have our general expression derived from our differential equation to be natural log of x equals t over 2 natural log of 12 plus natural log of 100. When you're substituting your value of k back in, be wary, because some people will put the t at the end, so put a half natural log of 12 t at the end, but when they come to substitute in, they will do natural log of 12t. which is not the same as what we're doing. We're doing that natural log of 12 multiplied by t over 2. Move the t to the front of the expression. Just make sure you don't make a hoolers, as they say of it. And the question asks us to find out how long it will take him to reach 100,000 xp, or x equal to 100,000. If I substitute those values in, I'll get natural log of 100,000 equals t over 2 natural log of 12 plus natural log of 100. Again, moving my natural log of 100 to the left and doing 100,000 divided by 100, giving me natural log of 1,000 equals t over 2 natural log of 12. I'll multiply across by the 2, give me 2 natural log of 100 equals t natural log of 12. Again, using the laws of logs, meaning that when it's multiplied by 2 at the front, I can move it round to the indice at the far side. So I'll get natural log of 1,000 squares. That should be 1,000 over there on the right side. Natural log of 1,000 squared equals t natural log of 12, which gives me the natural log of 1 million divided by natural log of 12. And that gives me 5.55977 hours, or 5.56 hours to 3 significant figures. And that's our expression worked through and used our original differential equation to get us an equation which we can use to problem solve or find something out. So step by step, that goes a little something like this. We're going to rearrange to create an expression we can integrate our expressions, and substitute in values to find k and c. Once we've done that, we can solve problems using your new expression, and those are your little step-by-step basis for it. Time for a commercial break.
And now it's time for a breakdown.
Nighttime. Daytime. Nighttime. Daytime. Nighttime. Daytime.
What are you doing?
Having a game of nighttime, daytime. You want to play?
Let's move on to some past paper questions from a CA point of view, and I've picked 2 examples out. First one is January 2009 from C4, and the question goes like this. A body is moving so that the rate of change of its distance from a fixed point A is inversely proportional to its distance x from A at any time. This can be modelled by the differential equation dx by dt equals k over x. Again, our variables for this question are x and t, so that it has some relation to the last question. It then goes on to say where k is a constant, given that x equals 100 when t equals 0, and that x equals 50 when t equals 5, find the total time the body takes to reach A. First thing we're going to try and do is visualize the problem if we can. In some cases, the differential equation will ask us to do something at the end of it, which will mean that you'll need to understand what the problem is first of all, or to visualize the problem is. What can we tell from the question? Well, given that at time t equals 0, x equals to 100 here, and that x equals to 50 when t equals 5, we can see that if we put a fixed point A there, and the body that we're talking about at the right, it's actually moving in a direction towards A. It's getting closer to A as time goes on. This means when find the total time the body times to reach A, we can make a determination at that point. So I'm going to stick our 4 steps down the left hand side here, number them and work through them. So we're going to rearrange to create an expression we can integrate. That was our original expression there, dx over dt equals k over x. And I can, if you want, cross multiply, but I hate that term because it leads to so many errors. So we're going to multiply across by the x and multiply across by the delta t. And we will get the integral of x dx equals the integral of k with respect to t. Remember that I said there was no variable in t before. We usually just leave the constant k over to go with the t. And that's the first bit done. Second bit, we're going to integrate our expressions. Should be quite straightforward. The integral of x with respect to x is x squared over 2, and the integral of a number, or k, with respect to t is just kt, and we'll stick our constant plus c at the end. And that's done as well. We're going to substitute values in to find k and c at this point. And we're told that when t equals 0, x equals 100. When I put those in, I'll get 100 squared over 2 equals k times 0 plus c. Give me c equal to 5,000. And when t is equal to 5, x equal to 50, using the x to be 50, t to be equal to 5, and we're going to use my value of c from 5,000 that we worked out previously, I'll get 50 squared over 2, which is 1250. And 1250 equals 5k plus 5,000, When I rearrange all that, I'll get k equal to 750, and there are my two values for c and k. With that done, we're just going to left to solve the expression. Our differential equation looks like this with our values of k and c worked out. We worked out k to be minus 750 and c to be 5,000. We were told to find how long it takes for the body to reach A, and x is the distance from A. So when the body reaches A, x is going to equal 0, and we would have seen that from our diagram earlier. So we're going to put x equal to 0 into our expression. 0 squared divided by 2 will just give me nothing. And when I bring the minus 750t over to the left, I'll get 750t equals 5,000. T will equal 6.67 seconds to three significant figures. And that is our question. Done. Okay, so that one bears a good resemblance to the example that we did earlier on. We'll do one more. Try to pick what was I considered to be the most difficult question from the slew of past papers that I have. It's from January 2013 C4, and it goes something like this. Now, I will say I'm not a big fan of this question because I think it's hard to know when you already know something whether you knew it beforehand. So I think this question means that you probably know something about radioactive isotopes and things about half-lives. Although you may be able to infer it, I may be incorrect in that assertion, but I don't think it was a great question for that very instance. But anyway, a radioactive isotope decays at a rate proportional to the amount A present at time t years. Form a differential equation to model this, and the half-life of the isotope is 250 years. So find the percentage of the original amount that remains after 100 years. Okay, this is a little different from the questions before because they don't give you a differential equation to start off with. So I'm going to step back and have a look at some revision from something that you've done beforehand. So the fact that you're not given a model to work can unsettle some students. However, this type of setup was introduced at GCSE. Do any of the following questions look familiar? Y is directly proportional to the square of x. Y is inversely proportional to x. These would produce the equations y equals kx squared and y equals k over x. They are GCSE higher topic questions, and ones that I generally find that students find very, very straightforward at the time. Using a lot of the same language above, you're looking for exactly the same keywords: square of x, inversely proportional to, cube root of x, anything like that. And as you'll notice, there's also the use of the k again and again. In this case, it says a radioactive isotope decays at a rate proportional to the amount of x. So A varies as directly as t in this case. So we're going to rearrange to get an expression so we can integrate, substitute in defined values, and solve problems. So the first part, we get that A varies as t is directly proportional, so it's Ka. Okay, just like your GCSE questions, when it's directly proportional, it's just k times that variable on the right A. And when I cross multiply and do all those things, it's nearly identical to the first example that we looked at, where we'll divide across by the A and multiply across by the t. So we get the integral of 1 over A with respect to A equals the integral of k with respect to t. Done. Next part, we're going to integrate our expressions. We get natural log of A equals kt plus c, just like we did beforehand. And we're going to substitute in values to find k and c. Well, we know that when t is equal to 0, the isotope is full. Now, you can call this whatever you want, this value of A. You can call it, 100% or whatever you want to call. I just put it as a value A0. Actually, took it straight from the mark scheme as such. I think I would call it full A or 1A or something. Whatever way you want to call it, so you'll have to be careful about later on. You call it A1, or it doesn't matter what you call it, X. So we're going to give it a value of the initial value of A, or A0. If we substitute those values in, we'll get natural log of A0 equals k times 0 plus c. Once we do that, we'll get that c equals the natural log of A0, or whatever we decided to call it at the start. Could have been x, or whatever. When t is equal to 250, A was half of its size, and this is the bit of the question I don't like. unless you're a physics student or some other sciences student, you might not have realised that. I mean, you may have. I have no real idea. But given that you're already modelling a as a variable within a variable, or it's like a constant within a variable, should I say, because you're using this a naught, I think that may have thrown some. I think that's what makes this question difficult. So a is actually equal to half of what the value was from the first part, basically. So a naught over 2. When I substitute those in, I'll get natural log of a naught over 2 equals 250k plus our value of c from before, which is a natural log of a naught. Rearranging, I'll get natural log of a naught minus natural log of natural log of a naught over 2 minus natural log of a naught equals 250k. Combining my logs together on the left again and rearranging, I'll get the k is equal to 1 over 250 natural log of a half, and I'm going to leave it like that, just like I said earlier. This is where the question gets a little bit tricky. We have got to find how long it looks, or how long, or how much it is depreciated, or what percentage of its original value it has after 100 years. Now, 250 was the half-life, 0 was when it was full. We're going to put our expression in to what we've got, remembering that we'll put our t in at the front instead of the end of our 1 over 250 natural log of a half. So we've got to find the ratio of a, so a to a naught when t is equal to 100. When I substitute t equal to 100 in, I will get natural log of a equals 100 over 250 natural log of a half plus natural log of a naught. I'm going to work with this little expression in here first, because we've got logs on the left, we've got logs in the middle, we've got logs at the end. We can actually combine these together and get rid of the natural logs if we want. It takes a bit of a, messing about's the wrong word, but a little bit of manipulation with algebra to get this far. So if I turn 100 over 250 into 2 over 5, and then use my laws of logs to take the 2/5 and make it a power, I will get natural log of a equals natural log of the half, which is 0.5, to the power of 2/5, which is 0.4, plus natural log of a naught. Using my laws of logs, when I add logs together, I can multiply them together. Once I do that, I'll be able to have a log on the left, log on the right. They'll cancel, and I'll just get a equals a naught times 0.5 to the power of 0.4. The ratio of one to the other, or the percentage increase, is going to be a divided by a naught, which is going to equal 0.7579, or 75.8%, the three significant figures. And that's the end of the question. Certainly some of the manipulation there at the end is a little more challenging, but like most difficult C4 questions, have a play about with the algebra that you've got there, and see what you can use to combine to get it in the form that you want. And that's that question done. Our objectives at the start of the lesson were to set up differential equations from a set of instructions, find the unknown constants k and c using given values, and solve problems using differential equations. We set up differential equations from a set of instructions, both when they give us part of the differential equation, and also when they just give us a general expression. We did that in the third example there specifically. We found the unknown constants k and c right throughout each of the examples, and we called it objective 3 in the questions, and solve problems using the differential equations. So showed that once you got an original expression, you could use it to solve and problem solve and find other values at other times. That is our lesson done. If you want to practice, there is a QR code with a link to all the CA past paper questions from 2009 to 2014, all grouped together for you to have a go through. If you have any feedback on the resources, send them to @flipmath on Twitter, or comment on the video below or on the website. Hope you found that helpful. I'll catch you next time. Bye.